minutos porque después de esta charla tiene que estar en otra, en 50 minutos.
Ok.
Salió. Él salió.
Saltar a otra sesión.
Él
Vamos a
tiene que
ver. Yo
estar.
creo que él va a intentar conectarse a otro dispositivo. Vamos a ver. O no sé, intentarlo de nuevo.
Bueno, vamos a hacer algo, chicos. Vamos a hacer algo. Escúchame los que están acá. No
Ajá.
alcanzamos a leer todo el discurso de él porque tiene que estar en 50 minutos en una sala.
Ok.
Entonces vamos a leer solamente el primer párrafo. ¿Listo, Milton?
Ok, está bien.
Vamos a ver.
¿Qué está hablando?
Apenas el profesor entre, lo hacemos cojos rápidamente. Pero ¿qué será? Qué gracioso. Porque o lo escuchábamos o nos escuchaba, pero una de las dos. A ver.
Sí.
Ok. El ICMAM acaba de compartir el link del canal de YouTube.
Me avisan cuando ingrese el profesor.
Estoy aquí pendiente.
¿Ingresó?
No,
No.
todavía no aparece.
Listo, ya le escribí. Bueno. Parece que... Bueno,
¿Será que debe estar teniendo problemas también con él?
es que creo que él tiene problemas de sonido, ¿no?
Exacto.
Esperemos al profesor hasta que se conecte. Bueno.
Listo, Duan se conectó. ¿Dui?
¿Me oís ahora?
Sí, te
Ahora sí.
¿Me
escuchamos.
oís?
Ujú.
Yo
Sí.
no os oigo, lo mismo que antes.
Listo,
No
entonces
sé qué problema hay, no os oigo.
vamos a darle continuidad, Duan,
Yo no os
a
consigo oír,
presentarse. Okay.
lo siento.
Entonces, en el chat escribamos profesor que presente la presentación, que comparte las slides.
Ujú.
Bueno, entonces voy a comenzar. ¿Esa pantalla es la del profesor? Sí.
Sí, comienza tú.
Buenos días en América y buenas tardes y noches en el resto del mundo. Mi nombre es Milton Manuel Aguirre, uno de los organizadores del ICMAM 2022, y para mí es un gran placer presentar en nuestra primera conferencia del día de hoy a una persona, a una de las personas con mejor conocimiento en el área de matemática aplicada, como lo es el profesor Enrique Subasúa, quien es actualmente el director de la Cátedra de Matemática Computacional del Centro de Investigación Deusto Tech de la Universidad de Deusto en Bilbao, País Vasco, España.
Good morning in America and good afternoon and evening in the rest of the world. My name is Duan Cardona, one of the organizers of the ICMAM 2022, and it is my great pleasure to introduce one of the persons with one of the best knowledge in the area of applied mathematics in today's conference. The Professor Enrique Subasúa, who is currently Director of Computational Mathematics at Deusto Tech Research Centers of the University of Deusto in Bilbao, Basque Country. So, Professor Subasúa, please go ahead.
Bienvenido,
Okay,
profesor
should I talk?
Subasúa.
Okay, can I start? Yeah. So sorry, sorry, Kari, sorry, Duban, sorry all. I cannot hear. I just relaunched my computer, and despite of this, the sound is not working. I really don't understand. There should not be so many options, but yeah, something is missing. So anyhow, I hope you can hear and see my presentation. I'm delighted to be here with you in Colombia. I was once in Colombia, in Bucaramanga, in person. Now I have the opportunity to be virtual, and I hope we can meet again soon. Thank you for the kind invitation. At present, I am in Singapore, so it's like 12 hours more or so. We are in the opposite sides of the planet, but despite of this, well, we can still communicate thanks to the global network. Well, maybe some of you have already heard this talk. I'm sorry if that is the case. Still, this is I'm in Singapore here to take part in a workshop devoted to machine learning, say mathematical aspects in machine learning. Maybe some people call it nowadays scientific machine learning, because there is a lot that has been done, in particular by the computer science community, and somehow mathematicians, we are lagging a little bit behind, right, on putting our analysis, our understanding of why these methods work, and trying to explain, the success of artificial intelligence and machine learning in particular, right? And of course, as every mathematician interested in this topic, if you really think on it, you will, try to figure out, so how could you contribute? So how can you approach from your own field of mathematics, whatever it is, analysis, partial differential equations, geometry, how can you contribute to such a vigorous and dynamic, say, contemporary topic as scientific machine learning? This is something I asked myself like 2.5 years ago, and we have been working in our group, trying to somehow exploit our know-how on the control of dynamical systems, in particular ordinary differential equations and PDEs. So this topic we presented, we delivered a lecture in the SIAM conference last summer in July in Pittsburgh, and you can find a short article in the last issue of SIAM News precisely on this topic. For those that don't have the opportunity to listen to the talk or want to learn more details, you can have a look to that newspaper article. So actually, control is a very broad field, very old. Even Aristotle already 2,500 years ago advertised, the need of humans making processes automatic so that the human can be more free. And it took a while until this became, say, a mathematical discipline. This happened essentially during the Industrial Revolution, where the contribution of, say, control, cybernetics, automatic control sciences, control engineering, whatever you call it, was so relevant, right? That, soon it was identified as a discipline. And still, even though, the applications were there, it took some more time in order to really, formalize the mathematical, say, body of this theory, right? And I like always to present this classical result by Rudolf Kalman back in the 50s, which exemplifies very well, I think, what people at that time had in mind. And that was a very solid starting point for a very, say, fruitful development of the theory afterwards, right? So, but before that, let me remind you how Norbert Wiener defined the field of cybernetics, automatic control. He said, this is the science of control and communication in animals and machines. And you see that when saying that, he identified two binomials, right? One is communication and control. So you need information to be able to act, to take decisions. So sensors on one hand and actuators on the other, there is this binomial, this duality. And the second one is animals and machines, precisely as Aristotle indicated. So we humans as animals, we need machines that will do our jobs, regular jobs, so that we are free to, for instance, be running this seminar, okay? But I don't need to take care of the thermostat, of the light, of the washing machine, the fridge, everything is automatized so that I can focus on this communication exercise. And when you see this definition, you wonder why, but I mean, this definition could also be the one of artificial intelligence to a large extent. And this is true. Actually, control and artificial intelligence, they really share the same, say, goals very early in their inception. So what Kalman said was the following. So assume you are trying to control a, finite dimensional dynamical system like this one here, right? A can be, say, the interaction matrix describing some communication networks, for instance, or it can be, the heat propagation matrix in the large building. I am in a large hotel here where there are many corridors, many elevators, many rooms, so they are all interconnected. And certainly, heat is diffusing and propagating and being transported, right, in the interior of this, say, building, right? And this is done through a communication matrix A that is taking into account how different, say, rooms are interconnected through, say, windows, doors, and so on, right? So we can think on the kind of dynamical system you can imagine. It could be also, 100,000 people, right, in the soccer stadium in Bogota, interacting each other. The system you like, it can be a discretization in a space of a partial differential equation so that you get a time, dependent finite dimensional system. Just to make things simple, let me focus on the case where A is time independent and linear, okay? But, these kind of ideas can be extended not without significant, say, analytical work to the time dependent, so non-autonomous and non-linear and even infinite dimensional system. Okay, so Kalman said, assume then we have a system where X, the state of the system, can have n components, x1, xn. It can be, the opinion of every individual in this social network, right? x1, xn, that is evolving in time because people are chatting, people are discussing, people are receiving inputs, they are changing opinion, right? So this is recorded in a vector x1, xn, depending on time. And we are able to, to feed the system through, the actuator, right? With some input vector u that has normally much fewer components, u1, um, right? It can be just the buttons with which you regulate, heat or the functioning of any of the devices you have at home, right? Of course, the number of regulators, the actuators you are playing with is much less than the number of components inside the machine, right? But then in order to understand how this control can operate the system, it's very important to know what the matrix capital B is, right? So the matrix capital B transfer, every time you make a small deformation and a small change on your actuation U in any of the components U1, UM, this is transmitted to the end components of the system. And then Kalman said, for the system to be controllable, the if and only if condition is that the rank of B, AB up to AN-1B has to be full. If the rank of this, say, iterated matrix is equal to N, the dimension of the space, it means the system is controllable. So it means that this engine, this vector, this particle X of t in the Euclidean space of N dimension can be driven, right, in any direction, in any time, and therefore can achieve any goal. This is the definition of control, whether you can steer the system from an initial configuration to any final one without any abstraction. And the lack of abstractions is precisely, recorded in this rank condition N. So, however, before that, there was already a pioneering article by Lord Maxwell, the same that, introduced the theory of electromagnetism, right? That said, well, he analyzed the behavior of the governor, is the ball regulation, mechanism, for the steam engine, the most, relevant, device in the Industrial Revolution. He already indicated in some examples, in particular analyzing the harmonic oscillator, that even though a system is controllable, the controls oftentimes are convoluted and do not really, obey our most basic intuition, right? And this is indeed in practice the case. Even when a system is controllable, it doesn't mean that necessarily because you push stronger, you will control the system better, right? So this is something you are on the highway, you are driving a car. I mean, there is some kind of risk. And then if you brake, too strongly, then you can destabilize the car and actually have an accident, right? So it's much better to, to brake smoothly or intermittently. Of course, it's against, it's not very intuitive. Our intuition is, as soon as we see a risk, is to brake like in a Dirac delta impulsionally. And this is what, our intuition says is not the optimal solution. And this is precisely the kind of remarks that Maxwell did analyzing the dynamics of the governor, right? So even when the system is controllable, it's not necessarily so easy to control, right? And then there are several, very elementary examples. This one, for instance, is explained very nicely in the book of Eduardo Sontag that you can download from the Springer webpage. This is the so-called Nexon car, in which he describes, listen, if you want to describe the dynamics of the simplest possible car, you need two parameters for the center of gravity, one parameter for the angle of the main axis of the car, another parameter for the angle of the wheels with the main axis of the car, right? And then you have four parameters, right, for this dynamical system, while you have only two controls, the gear and the accelerator. Yet, if you go to the, to the auto school, after a few classes, you will learn how to drive this engine. And this shows you that with two controls, you can control a four-dimensional system. As I said, this is not necessarily easy. Now, if you really compute, a control trajectory, right? In this case, for an articulated car, right, a truck, you see that when you compute optimally the trajectory of this car that has to go from, this vehicle that has to go from this configuration to this one without exiting this box, you see it has to develop this kind of oscillatory sinusoidal trajectory, forth and back in order to go from this configuration to this other one. Of course, if you will not put the bounds of, the car or the truck remaining within this, parking, if you let me, travel freely on the plane, I will rather do something much simpler that even myself will be able to do, right? So I will turn around, right, along a long circle, and eventually I will come back again and then, set up the car in this configuration. So this also shows that when a system is controllable, there is not one single control. There are many ways of controlling, in particular, this track, right? But if you want to do it optimally, if you want to do it, for instance, within this parking lot, or you want to do it by, by a trajectory that is not too long, by the trajectory of minimal, say, time or the minimal length, then you will have to really develop this kind of complex strategies that normally in control systems can be only understood once you analyze the optimality system of Pontryagin, and this is something that can be analytically complex. Of course, there are other ways, this is the impulsional way of controlling or parking a car, right? But this is not accessible for everyone, okay? So this was a brief introduction for control. Now, I mentioned in the beginning, and you already see that in the very definition of Norbert Wiener for cybernetics, that there is some, analogy on the goals of, say, artificial intelligence, machine learning, and control theory or cybernetics. So in order to show that this is really the case, and this is something that we, analysts, mathematicians, from our perspective of applied analysis, we can really understand that. Let me tell you briefly about probably the simplest and the most classical paradigm in machine learning. This is the so-called supervised learning. Right? So in supervised learning, the goal, let me just put it in this example very simply, the goal will be to build a machine so that, this machine will classify trash automatically without the need of human intervention. So then you see, you have on trash, you have plastic that should go to the yellow basket, glass that should go to the green, paper that should go to the blue, and biologic, organic that should go to the gray. Of course, this is something that we humans can do. I mean, you leave me a bunch of, items, I can check one and say, oh, this is a sandwich. This goes to the bio. Oh, this is a newspaper. It goes to the blue. Oh, this is a beer bottle. It goes to the green. Oh, this is a plastic bottle. It goes to the yellow. I can do that myself, but I don't want to do that. I prefer to do math. So I want to build a machine that will be able to do that. So how do we do that? What is a machine, first of all? Well, a machine for us is a function. It's a function that allocates to each item the corresponding target. F going from X, say items, into Y, labels. Label being, yellow, green, blue, or gray. Of course, I can, place these labels on just the real line and say, yellow is -1, green is 0, blue is 1, and gray is, say, 2. That's very easy. Images, labels are just points in the real line, okay? Good. Now, what about the items? I could say, well, items are shapes, are, say, objects, physical objects. I can just take a picture, make pixels out of it, and then every item will be an image, will be a point in a Euclidean space of large dimension, depending on how many pixels I put in this image. Maybe not very, not very high resolution in this case, but still several hundreds of probably pixels in order to have a good, say, image of the item we are considering. So the X's will be in a space, Euclidean space of dimension D, large dimension. The labels Y will be in a Euclidean space of dimension M, probably very low, even dimension 1, just the color, okay, allocated through, say, a point on the real axis, on the horizontal axis. And then it will have a number, capital N, of items. And then the question I ask you is, can you build a function F so that to every item I allocate the corresponding label? And you will tell me, yes, of course I can. I mean, I can do polynomial interpolation and I can get it. Now, the problem of polynomial interpolation is that this function will be very oscillatory. And then you will tell me, well, Enrique, you didn't say anything about oscillations. In principle, if the goal is just to interpolate, I can do it. Yes, but recall that the goal in machine learning and in control theory is to build this machine or this function so that later you can use it with the purpose of generalization. So what does it mean, generalization? It means that once the machine is built, once this function is built, you can simply next time, whenever it brings you, someone brings you a new item, you will say this person, just place it in the machine. And then the machine will take this item, and then according to the function f, this, this machine, this function will allocate to this new object x a label that is, the closest one to the others you have, and will immediately determine whether this is a plastic bottle or a glass bottle. So you want this function not only to interpolate the data you have, right, supervised learning, but to learn well so that you can later use it for, generalization without paying too much oscillations and in a reliable manner. In '89, there was a paper by Sivenko in which he introduced the so-called universal approximation theorem. For analysts, this is just a density result, a very nice one, right? But we know many others. We know that Fourier series are dense. We know that polynomials are dense, Stone by Strass, right? So there are many other classes of functions that are dense. Say infinity and compactly supported functions are dense. What Sivenko said, functions of this form are also dense. What are functions of this form? This is very simple. You take a sigma function, a so-called activation function. So this is sigma. In this case, I adopt the so-called ReLU. In machine learning, they call it ReLU, rectified linear unit. It's a complicated name for a simple function, right? It's the function that is simply taking the value x plus 0 to the left and linear to the right, okay? So this is the function sigma. And then with sigma, you will cook a combination using some parameters. You will cook a combination of k of them, k being large. Of course, like in a polynomial, you need high order to get approximation, or in a Fourier series, you need to pile up many trigonometric functions in order to get density. Here is the same. You take k of them, capital K of them, and k, capital K, will be typically large, okay? And then for every term in this sum, finite sum, with a large number of terms, you will regulate, this sigma by choosing the amplitude I place in front. You will also translate the variable x, right? So that the cutting point, rather than being at 0, can be located anywhere. And you will also scale, stretch, dilate the variable x so that you can regulate the amplitude of this slope. I mean, the slope of this linear function. What Sivenko said, this set of functions is also dense. And the paper by Sivenko, '89, is beautiful. It's very easy to read. It's beautiful. It's just an application of Ham-Banach, but it's very smart. And indeed, this is something that we can understand. These functions are dense. And now, when you superpose, you draw what this means, you will realize that basically what this function will be in this particular case of the ReLU. So Sivenko did it for more general, say, sigmoidal activation functions, as according to his terminology. If you do it for the ReLU, what you see is that you have piecewise linear and continuous functions, in which you are basically, choosing the points in which, the lines are being broken, right? And the slopes of the corresponding of the different lines. So it's not so hard to understand analytically why this class of functions, like simple functions, for instance, are indeed dense. Now, this, supposed a revolution in the context of artificial intelligence and machine learning, because people said, well, if these functions are dense, whenever you ask me, for instance, in the context of supervised learning, that I have to build a function that is interpolating on this point, so why don't we simply look for it in these particular ansatz? And this is what people said. They said, let's adopt these ansatz because they are dense. I know if I take k large enough, I can maybe not exactly interpolate, but I can interpolate as close as I wish. And then we will be building a class of then function. Among them, there will be the function we like that is interpolating this data. And this time, because this will be a linear function, right, interpolating the data, this will not be that convoluted. So the generalization property should be better than, for instance, for polynomials or Fourier series. Right? That was the idea. Now, the question, of course, once you adopt this ansatz, is how you compute these coefficients. But then these coefficients bj, aj, wj are typically computed using the computer, I mean, just by optimization tools, by simply a least square algorithm. Because you want to guarantee that the function f is so that f evaluated at xi is equal or very close to yy, I will simply penalize the distance square. I will sum with respect to all, say, items I have in my supervised learning exercise, and the minimization of this multi-criteria optimization function will lead you to the needed coefficients. So soon after, people like Eduardo Sontag and Sussman, experts in, say, dynamic control, much more recently, this topic was revived by, Wayne and E and collaborators and several others afterwards. People said, well, rather than doing it in one shot, piling, this neural network in which capital K, is very tall, and I have to accumulate many neurons, why don't we try to organize our, workload into different time steps? And then people consider the so-called residual neural networks. Basically, in the residual neural networks, you are doing the same, but now along a time discrete dynamical system in which in every step from K equal to 0, the initial configuration in which the item is originally given, to the final one, these images are traveling in the Euclidean space until each of them lands in the corresponding basket according to its label. So yellow for plastic and so on. People said, well, let's try to do that. But actually, if I do that, and we call this residual, why? Because you see here that in every, say, time step from K to K plus 1, I'm taking here the identity operator plus a perturbation that is small in amplitude. People observe that if we think on this small parameter h, which justifies the terminology of residual, we think on it as being delta t, the time increment, then we are considering a time discretization of this ordinary differential equation. And then once also the parameters b, a, and w become, continuous in time, we realize that this is a control problem. And people said, we are on the boat. We know everything about control theory, and this is a control problem in which the goal is to choose the coefficients bt, wt, and here it should be at, and here wt, right? So this should be an a, bt, at, and wt, so that every item goes to the corresponding basket. But if you think on it a little, you realize that this time, contrarily to the classical, say, problem of control in which, for every item and every destination, I'm choosing one single control. In this case, I have a whole cloud of points that I have to control simultaneously, right? Because the same controls, the same machine has to be able to classify all items regardless of what the corresponding label is. So it's not true that this is a standard control problem. Actually, this is a super, say, control problem in which we have to simultaneously control all the trajectories corresponding of all the data to all the data that I'm given in the supervised learning exercise. Okay? So this is the so-called supervised or ensemble control problem for this nonlinear differential equation in which the nonlinearity is the same sigmoid appearing in the neural network. In our talk, it will be the ReLU, right? And in which, as I said, the main difference with respect to classical control theory is that all items have to be controlled simultaneously. Can we do that? Well, and the answer is yes. So you can find several of our papers online. For instance, this paper with Domenech Reed-Vallet, in which we prove that indeed this simultaneous control property can be achieved. There are other papers in which we go further and we explain how this fundamental result can later be used in order to explain and to analyze the behavior of the deep neural networks, right? But for this talk, I would like to simply, explain you heuristically the main idea of the proof of the fact that yes, we can. These, say, deep neural networks, these residual neural networks or neural differential equation are, able to fulfill the tasks that, we require in the context of supervised learning. Okay, so how do we do it? Well, the idea is very simple. Basically, these neural ordinary differential equations or these residual neural networks really behave like a Rubik cube. And, some of you have already solved the Rubik cube. Some others never did it, like myself, but I have seen some others doing it. We know how it works. So you give this kind of disorder random initialization for the Rubik cube. And then the goal is to, you see, it's very similar to the problem of classification in supervised learning. The same of classifying trash, right? Because we want to bring this Rubik cube into a configuration in which every face is homogeneous in color, right? Every micro faces that are read have to go to the same face. And then we have to, build the homogeneity of the Rubik cube according to this, say, coherence on color on faces, right? And the way we do it is on a finite number of steps. And in every step, we do a control action, which is piecewise constant. Every step is constant, and then we accumulate different constant actions, in which in every action, what we do is we fix half of the cube, and on the other part rotates according to our decision of what is the strategic, say, direction of rotation and angle. Okay, so you see that the Rubik cube is solved by the concatenation of a finite number of piecewise constant actions in which half of the cube or part of the cube is fixed and the other one is rotated. And this is what we do. And this is, for instance, a simulation done by our colleague Borjan Geskowski, now a postdoc in MIT, in which you see that if you ask the computer to do it, the computer finds, the solution of this problem to this problem in this context of neural ODEs. So you see here an exercise in which there were 3 different labels, purples, greens, and yellows. We started from a, say, disordered, right, structuring of the data. And along time, coherence emerged. And you see how the dynamical system is able to classify data according to color, so that purples are here, green are there, and yellow are over there. So why these neural ODEs are able to fulfill this exercise? The reason is the following. If you think on this ordinary differential equation and you keep in mind what the sigmoid sigma, the ReLU is, so 0 to the left and linear to the right, you start gaining an intuition of why this is going to work. The reason is the following, right? So at every time, when you look to this ODE, you immediately realize there are 2 options. Either X is on the side where sigma takes value 0, and then in that case, X prime is equal to 0 and X doesn't move, right? Or X is on the side where sigma is active, you are in the support of sigma, then sigma is a linear function, and therefore this is a linear ODE on X in which the response is exponential. So you see that, in the Euclidean space dimension D, A dot X plus B equals 0 is just a hyperplane that is dividing the space into 2 hemispheres. So what we are doing by this neural differential equation at every time, by choosing the parameters B and A, is to determine a hyperplane in the space that is dividing the space into 2. And the ODE is understanding that, the corresponding evolution of the space should be according to the hemisphere, frozen on one side, so fixed X prime equals 0, and exponential motion in the other. Very much like the Rubik cube, right? Now, as I said, A and B are just, the parameters that allow me to choose at every time the hyperplane in which I'm carrying the space into 2. And W is the wind that will push the mobile, the mobile half of the space. W will choose the direction in which you want the wind to push. And then you can generate motions like this, for instance, but many others as well, in which you say, for instance, the cutting plane is the equator, the south is frozen, and then the north can evolve in any direction, north, west, south, east, for instance. But you can also do it according to any oblique hyperplane and any other, say, diagonal direction as well. And once you realize that, you observe that you can indeed solve the problem of classification like you do it in the Rubik cube, in an inductive manner. So what do I mean by an inductive manner? I mean that I really don't mind how many points capital N you give me. Of course, if capital N is very large, building this machine that is able to classify all these items will be very laborious. But it doesn't matter. We have an induction argument, and then we know that regardless how big capital N is, we will be able to do it. We can do it in any dimension D of the Euclidean space, provided the dimension is more than 2. Otherwise, in 1D, it's very hard to, classify items because they collide whenever I need to swap their ordering, right? So I better am in 2D where I can, swap the ordering without collision. And I also don't mind how many labels there are, right? How many, different baskets, different criteria according to which the data have to be classified. The theorem is quite general in this respect. But let me show you how it works in a very simple example. So here we are in 2D. We have points in 2D. We have N, so D, the dimension D in this case is 2. The number capital N of items is 9. There are 3 labels, blue, red, and green. And in this case, the baskets are placed horizontally in bands, like this: blue for the blues, red for the red, and green for the greens. And then the goal, of course, in this classification problem is to build a function that will take all these points and will place them in the corresponding, say, band, right, basket, according to their colors. When you see this picture and you see the destination, you say, well, it's almost done. I should simply translate it to the right. I should take this cloud of points and translate it, and they will fit in the corresponding, say, reservoirs, except maybe for 1 point. Why? Because this blue is clearly surrounded by the reds. So the goal in this induction argument, right, is to show you, this will be one step in the induction argument, how facing this situation, you can, despite of the fact that the blue is surrounded by the reds, how you can rescue the blue from the reds and bring it back to the basket corresponding to the blues. In order to do that, you will just use this data as initial data in our, say, neural differential equation. And I will have to choose the controls as in the Rubik cube, piecewise constant. In this case, I will need 3 motions. In each motion, the control will be constant and will be chosen strategically. So to, in 3 steps, as I anticipated, I will succeed of making, the blue free from the tyranny of the reds. How can I do that? Well, I do it in 3 steps. First step, I choose A and B so that the equator is just above the blue point. I can always do that. I can choose the point, the equator just above the blue. And then I say the south will remain frozen and the wind W, will push the north to the left. When doing that, after some time, I will see this configuration because you see the blue with the red and the 3 greens will be frozen, while the other 2 blues and other 2 reds will move to the left. once this configuration is achieved, in which the two lefts, surrounding the blue from the north are really, to the left, I stop the process and then I change mine. In the second motion, I take the equator, I shift it below the blue horizontally. I decide that the north will be frozen and the south will be moving to the left. In this way, the 4 points here will shift to the left. After some time, I will be in this configuration in which, the blue is to the right of all others. I will then choose the vertical hyperplane to the left of the blue. I will determine that the left is frozen, the right is going up, and in this way, you will see that the blue goes to the corresponding basket. So I have shown you how you can classify one item, and then the theorem says, if you do that inductively, you will get always given an arbitrary cloud, capital N of points in RD, D greater or equal than 2, and regardless how many, say, labels P you have, you can always classify points, endpoints, according to these P labels in RD with a control that will be piecewise constant, and therefore, in particular, with a finite number of jumps, and therefore also of, say, bounded variation. Of course, when you run the simulations, you don't necessarily see the controls I told you, right? So the controls I told you is a mathematical construction of the existence of the controls, right? Of course, if you want to visualize how these controls are, you have to do it in the computer, and this is when you see this kind of complex dynamics. But I repeat, this complex dynamics is not necessarily the one we are building, right, in our, say, proof strategy, a strategy of proof, because I have explained, as I have explained in the beginning, for the, the driving the track, there is not only one control strategy, but very many possible, right? And whenever you use the computer to compute one using a minimization strategy, the strategy you find will be the one that is adapted to this cost function that you have chosen, and is not necessarily the one we have shown in our, say, theorem, which is meant just to guarantee that indeed, the great goal of supervised learning can be achieved using control theoretical tools in the context of these neural differential equations. Just to conclude, I wanted to, make the link with another important topic, which is the one of, optimal transport. As you know, Monge formulated the problem of optimal transport as transporting mass or transporting goods, transporting sand, or transporting, furniture from one apartment to another, or transporting, goods, right? It was Kantorovich who, Nobel Prize in economics, who made the breakthrough of introducing relaxation in the problem of optimal transport. And in this way, right, he developed the mathematical theory of transport in economics, which allows, for instance, to organize, the income tax systems in which every citizen in every country is distributing, is giving back to the, to the state part of the earnings, so that the state redistributes, this wealth among the different citizens according to their wealth and their necessities, right? So this is a much more complex, relaxed transport system in which, all, citizens cooperate on transporting wealth from, the whole community, again, back to the whole community, but in a way that, this wealth is redistributed. There is clearly a link in all we said between, say, control and machine learning, also with optimal transport, right? Because, you can easily think on this in terms of characteristics for a transport equation. Indeed, if you are in the context of transport equations, right, in which mass is distributed from the initial distribution to the final one, right, then the solutions of the transport equation, as you know, they simply travel along characteristics, and the characteristics are precisely the solutions of the corresponding ODEs. Because we were able to show that in this ODE setting of neural differential equations, we can build controls, B, A, and W, that are able to simultaneously control, an arbitrary number of finite particles, and that, the finite combination of Diracs is dense. This means that you can, in an approximate sense, control also, in the context of transport equation, any initial distribution of mass into any other, linking and building the bridge towards optimal transport. The same can be said about normalizing flows. This is another concept also in the context of machine learning that is often used in order to, say, precondition, the probability distribution of the data you are manipulating, and in which, again, the goal is to, transform one probability distribution into another one. You can, again, understand it in the context of optimal transport that is equivalent, right, to, up to an epsilon factor to the property of simultaneous control we have shown, right? So in this lecture, I have shown you how the traditional goals of control and cybernetics match very much with the modern, say, objectives of machine learning, but that this, say, analogy and this, say, self-intersection not only arises at the level of the main goals of the theory, but also on the mathematical tools you can use, and that, in particular, using the techniques developed in analysis and geometry for the control of dynamical systems, you can understand some of these fundamental problems in simultaneous and control and supervised learning, building a path towards optimal transport and normalizing flows. There is, of course, plenty of interesting questions to be understood. This is just an invitation for everyone, right? Regardless of what your field of expertise is to, to keep an eye on the development of this field in machine learning, in which, I'm confident you have also yourself plenty to do and to say. Thank you for your attention, and sorry again for not being able to hear in your voices.
Okay.
Thank you very much.
Thank you, Professor. Very interesting, your talk. Okay.
Yeah, so we are running out of time, but maybe I just answer to Alexandra before I jump to the next meeting. Alexandra is asking how much our world depends on the control theory. Well, actually, we are doing control all the time, right? So we don't realize it. But, as I said, the thermostat, the washing machine, the frigo, every device we are using, the car, the bicycle, every mechanism we are using in office, everything is embedded within this complex system in which there are plenty of sensors and actuators. You see, I'm not able to listen to you because for some reason, one of the actuators, right, is not working well, right? So it's the actuator that should be, transferring your acoustic signal to me, right? Despite of this, we are being successful, but only 90% because of this specific actuator is not working. So control is everywhere, right? We don't realize it. In the regulation of, I don't know, traffic, of trains, of cars, airplanes, telecommunication, in every industry, every process needs to be controlled in order to operate successfully, optimally, in the given time, within the given bounds, so operational bounds, cost, personnel, etc. Everything in our modern society is under control. And, when we are not able to control a system well, we know that, accidents may arise, catastrophes may occur. Well, hopefully we still have a chance to, to recover later. But definitely this is a theory that is growing, right? As every mathematical discipline is growing, because we are living in a world that is more and more and more complex. and the challenges that are presented to us are also, you know, increasing in complexity. Okay, so thank you again for your attention. I will be happy to answer to further questions by email. Don't hesitate to send a note, and I will be happy to give you my feedback. Thank you again. Thank you all. Bye. Ciao.
Okay, so after the talk of Professor Suazua, we will come back to 9 a.m. in Colombian time to the talk of Professor Bolis-Silver, and in Central European time, we come back at 4 p.m. So, do other members of the organizing committee have some recommendation? ¿Tenemos alguna recomendación que hacer para el resto?
De mi parte, no.
Ok, muy bien.
No.
No, ninguna. Nos vemos dentro de una hora.
So, see you in 1 hour.
Yes.